Greetings, calculus students. I do believe I have my technological problems sorted out now that I'm at home on my laptop. Today in class, we worked on some problems on linear equations. I apologize for not being able to run you through a lesson before you got started, but being a remedial lesson, I think most of us were in good shape after we did a little bit of Q&A. But at any rate, I promised you a recording, so here it is. Our objective for the day was the student will regain a complete understanding of linear equations and their properties. Our language objective is the student will display the ability to work with and convert between the various forms of linear equations and identify critical pieces of information to their graphs. And the essential question for the day is, do I understand the forms of linear equations and the properties of parallel and perpendicular lines? Okay. Now, as you've heard over the years, basic information here, a line needs two things in order to do what it does. Obviously, it needs somewhere to start, and historically, this has been a y-intercept. From there, it needs somewhere to go. Historically, this has been a slope value. Okay, so that's where slope-intercept has become or always was such a tremendously powerful piece of information or equation for us to work with, simply because it provided these two things point blank in the equations. Now, different forms of equations have reared their heads over the years, and those different forms of the equations represent different information differently and in different places within the equations. Okay, it kind of begs the question why we even have so many forms if basically the information is kind of transferred to different spots and represented differently and things like that. However, as you will find, each of these different forms has a particular application, a particular branch or position in mathematics where one form is more desirable as compared to a different form. Okay, all of these forms need the basic concepts of slope and at least one point on the line. Now, as we can imagine, and as we will see here shortly, that information can be portrayed in a lot of different ways, but slope is kind of a critical aspect. And one of the things that makes slope as challenging as it is the fact that there are a lot of different synonyms that go along with the term slope. Obviously, there is the word itself, slope. There is the algebraic variable m, which represents slope. You're familiar with that one mostly from slope-intercept form, y equals m, x plus b. Rise over run is more than likely the vocabulary that you became familiar with slope on back in junior high. Okay, that vocabulary became a formula, which was m equals rise over run, and that formula, of course, was represented by the difference of the y's divided by the difference of the x's, and all of that information kind of translates directly back and forth across that row of representations there. As you've kind of grown up and developed some new mathematical skills and things like that, you've run into some word problems, and it's possible that word problems have come out and actually said things in basic word format here, like change in y over change in x. Okay, the word problems from time to time will actually state things that way. In a more physical type notation, we run into things like delta y over delta x. Through your travels in physics, of course, you should know that delta means change in, so that represents change in y over change in x, exactly like the green part there on the screen. And the kind of flavor of the month that has come around here in the last half decade or so is they do like to refer to slope as rate of change. Okay, so watch out for that one. Okay, now a lot can be told just from observing the slope value in an equation of a line. Okay, so hopefully you have kind of become familiar with a lot of these different values, so bear with me as we roll through them. A slope value can always be positive, which of course means the line rises as it moves from left to right. Now, if we have any choice in the matter, we always read graphs rising from left, or read graphs from left to right. If it's a positive slope, then it is rising from left to right. And of course, if we're looking at a slope that is negative, then obviously the graph is falling from left to right. Now, when it comes down to a discussion of parent functions, of course, the parent linear function would be a slope value of 1. So let's say we look at a slope value that is actually smaller than 1. What that means is the slope fraction, its denominator, is moving faster than its numerator. And when that happens, you're going to get a slope that is, or a line that is not quite as steep. So you get a line that is more horizontal than vertical when your slope is smaller than 1. The flip side of that is you could have a slope value that is larger than 1. That happens when you are rising faster than you are running. So the y value is increasing faster than the x value. That's when you get a line that is closer to vertical than it is horizontal. We run into things like this. Some of the old vocabulary that you might have run into is zero slope or no slope. Now, if you've heard these terms before, especially the term no slope, what we're going to need to do is we are going to need to dump that term. Once upon a time, the term no slope was an acceptable term, but here in recent history, they've decided that no slope is a bad term. We want to use zero slope to describe the condition where a line is horizontal. Horizontal line is running just fine. It refuses to rise. That means the numerator of the slope is 0, while the denominator is just some number. And if you put the 0 or a 0 in the numerator of a fraction, then you have a value of 0. Saying no slope would imply that it actually doesn't have any slope whatsoever. Well, this line does have a slope. Its slope is 0. Then also we have the flip side of that. We have undefined or infinity as a potential slope value. And this happens when a line is rising just fine, but it refuses to run. That puts a 0 in the denominator of our slope fraction. And of course, 0 in the denominator is an undefined fraction, meaning we have no language to describe what a 0 in the denominator means, so we call it undefined. Okay, so let's take a brief look here at a couple of points, and we're going to apply the line that connects these 2 points several times here in order to demonstrate the different forms of equations of lines. So we'll start off with the obvious piece of information. What is the slope of the line connecting these points? Now I'm going to offer you a very basic strategy that I even offer all the way down to even the lower level math students that I have. Anytime you find the need to use a formula, basic strategy would suggest let's go ahead and write that formula down. We don't want to try to be plugging information into a formula mentally and then writing the information down. So let's get that formula on our paper where it belongs so that we can then plug into it. Also get the information that you're going to plug into that formula on the line. In this case, we have 2 points on the line, 5, 9, and negative 5, 3. Let's write those down in the same basic location as the formula we just wrote down. And, comma, if you, pardon me, I'm used to doing text vocal here. Okay, if you're having problems with plugging things in or sometimes plugging things into the wrong place, what you may want to do is go ahead and get in the habit of any of the formulas that use this x1, y1, x2, y2 notation, like the slope formula or the distance formula or midpoint formula. Let's get in the habit of labeling these points. So 5, 9 and negative 5, 3, Those are point 1 and point 2. So let's label them x1, y1 and x2, y2. How do you know which one is point 1 and which one is point 2? Well, it really doesn't matter as long as whichever one you call point 1 gets the x1 and the y1. Whichever one you call point 2 gets the x2 and the y2. Just don't mix and match. You can't have one point that you're calling x1, y2 and the other one calling x2, y1 or anything crazy like that. Once you have your formula and your points and your labels written down, it virtually becomes impossible to not plug in values in the correct location. In this case, we got 3 minus 9 over negative 5 minus 5. Straightening up the algebra a little bit, negative 6 over negative 10. A double negative makes a positive, and the fraction reduces to 3 over 5. The slope connecting these 2 points is up 3 over 5. So what is the equation of the line in point-slope form? Well, of course, point-slope form says y minus y1 equals the slope times x minus x1. Well, we already know what the slope is, and we have 2 points to choose from, as far as the x1, y1. Now, which point do you choose? It really does not matter. And this is one of the oddities of point-slope form, is that if you ask 100 people to write down point-slope form of a particular line, it is feasible that you would get 1,000 different answers, and every single answer would be the truth. In this case, I just took the very first point, y minus 9 equals 3/5 times x minus 5, plugging in directly from the slope and the very first point into point-slope form. What is the equation of the line in slope-intercept form? Well, obviously, slope-intercept forms, the one we're probably the most familiar with, y equals mx plus b. Okay, we already know what the slope is, and we have 2 points that are on the line. Now, we do not know what the y-intercept is at this point, but we're absolutely going to need to know it. So that means that in slope-intercept form, we're going to need to plug in for the other 3 variables so that we can solve for b. That means we need a y, we need an m, we need an x. Well, we already know what m is. As far as x and y, we select either one of the points that we have available to us, and we plug in. So in this case, I took the second point only because it has smaller numerical values to work with, and I plugged it in. So negative 5, 3 got plugged in for x and y. Simplifying the problem a little bit, on the right side there, 3/5 times negative 5 is negative 3. And then if we proceed to isolate b, we end up with b equals 6. Plugging back into the original equation, we already knew the slope was 3/5, so we have an equation y equals 3/5 x plus 6. What is the equation of the line in standard form? Now, this was a question in class today. What exactly is standard form? Well, standard form is the format where you have all of your variable information on one side of the equal sign, all of your constant information on the other side of the equal sign. Well, right now, what we're working from is slope-intercept form. So what we can do at this point in time is go, let's move those x's to the other side of the equal sign, out in front of the y's where they belong. Okay, and then one of the things about standard form is that your lead coefficient for x there, it should be a whole number and it should be positive. So what we would probably do there is multiply the entire equation by negative 5. That would take care of the negative sign in front of the lead coefficient, also take care of the denominator of the lead variable there, and we'd end up with 3x minus 5y equals negative 30. There is your standard form. What is the equation of the line in general form? Well, we had questions about this one in class as well. The only difference between standard form on number 4 and general form on number 5 is that in general form, everything is on one side of the equal sign. So the only thing really left for us to do at this point is to take that negative 30 from the right side, move it over to the left, and there is your general form. 3x minus 5y plus 30 equals 0. Last thing to look at here is how lines behave with each other inside of a graph, and that is the topic of parallel and perpendicular. Hopefully you remember if two lines have the same slope value, that means they are going to be parallel, which makes perfect sense. If they are the same slopes, that means they are rising and running at exactly the same speed. In that case, there's no chance that they will ever intersect each other. Then you have perpendicular. In order to be perpendicular, they're going to have to be heading in opposite directions from each other, meaning one slope will have to be positive and the other will have to be negative. But in order to hit and form that right angle, those slopes have to be reciprocals of each other. So we're looking for two lines that have slopes that are negative reciprocals of each other in order to be perpendicular. So let's say we have a line passing through 2 points, in this case negative 2, 6 and 3, 0. And the question is, what is the slope of the line that is perpendicular to this one? Well, we need to know what the slope is connecting these 2 points. So again, a good strategy would be to write down your formula, write down your points, label your points as x1, y1, x2, y2, and then plug in your numbers. Simplifying this fraction, we've got negative 6 over 5. That's the slope of the line connecting these 2 points. So any line that wants to be parallel to these two is going to have to be negative 6, 5. But the question was, what is the slope of a line perpendicular to this one? Perpendicular means negative reciprocals. The negative reciprocal of negative 6/5 is positive 5/6. So that's going to be our answer. Okay, so that basically concluded the second of the prerequisite little sections that we had been hinting at that we needed to get it done. And there is the assignment that ensued. Now, anytime you see these little instructions that I give you, if I don't give you instructions about what to do on a particular number, that means to just follow the instructions that are in the book. But if I give you particular instructions like I did on numbers 41 and 42, that means to basically disregard what's going on in the book's instructions and instead follow mine. Okay, I apologize for the delay in getting the notes to you and the recording to you. Doing the best I can with the first week of school and the technology problems I've been having. Hope it didn't cause too much problem for you.